All right, in this video, we're going to be going over trigonometric substitution, but we're going to be looking at three special cases. And within these cases, we're going to have the following. So we're going to have integrals that contain expressions of the form the square root of ax squared minus x squared, the square root of ax squared plus x squared, and finally the square root of x squared minus a squared. And all of these occur when a is greater than 0, which if you think about it, no matter what, when you make your substitutions in for the letter A, since you're squaring the number, it's going to be positive anyways. All right? So let's just consider this case right here. Let's look at the integral of the square root of 9 minus x squared. Now, the way that this integral is set up right now, we cannot integrate this using any of the techniques that we have. It's just impossible. However, if we were to sit here and make this substitution, let's let x equal 3 sine theta, and then we take the derivative of that, dx equals 3 cosine theta d theta, and I'll show you how to get these in a second. If we were to do this and then make these substitutions, watch what happens here. All right? Our integral of the square root of 9 minus x squared dx turns into the integral of the square root of 9 minus the quantity 3 sine theta to the second power multiplied by 3 cosine theta d theta. And now, if you look inside, or better yet, if you look underneath the radical, there's some simplifications that can happen there. For example, and I'm gonna really just draw this one out here so you can see every little step, but they're pretty much all done the same way. First, we're gonna square 3 sine theta. So that gives me 9 minus 9 sine squared theta. Next, both terms underneath the radical have a 9. So we get the integral of 9 times 1 minus sine squared theta times 3 cosine theta d theta. Using our properties for radicals, we can separate them as such. Okay? And then finally, going from left to right, the square root of 9 is 3. Now that square root of 1 minus sine squared theta can be rewritten as cosine squared theta. Next, I can simplify the square root of cosine squared theta. I can also multiply the 3 times 3 and move it out front. So we're going to put a 9 out front. The square root of cosine squared theta is cosine theta times cosine theta d theta. And finally, you get 9 times the integral of cosine squared theta d theta. Now, in the previous section, we learned how to integrate cosine theta d theta, which what we would have to do is change this to the integral of 1 plus cosine 2 theta all over 2 d theta. And then you'd have to integrate this accordingly using use substitution and everything. But I'll leave that for you to do as an example. The big idea that I want to go back to is all the way back up here, which is how did I know to make these substitutions? Okay? And it all goes back to, and I'm going to scroll all the way back down, to nothing more than just right angle geometry. Now, one of the things hopefully you were kind of looking at is when I wrote the original problem, the square root of 9 minus, the integral of the square root of 9 minus x squared dx. This right here has that form at least hopefully you're thinking about it, of the top half of a circle. Because remember, x squared plus y squared equals z squared. And in this case, I could solve, let's say, for y squared just by subtracting a squared from, or x squared from both sides of the equation, okay? So this is the trigonometric substitution part. So what we're going to do here is this. We're going to put theta in the lower left-hand corner. And remember what sine theta represents. Sine theta is going to be opposite over adjacent. So in this case, sine theta is going to equal the opposite over the adjacent. That's the ratio. And then if you were to solve this right triangle using the Pythagorean theorem, this would be a squared minus x squared. So that's the way we're going to think about this. All right. In fact, if I scroll all the way back up, maybe you can look at these and say, okay, well, if I have the square root of a squared minus x squared, I'm going to make this substitution right here, which is sine theta equals x over a. Now, oops, don't want to do that yet. For the middle one, we're going to use tangent theta, which is going to be x over a, but in this case, the x is here and the a is down there. Because remember, tangent is adjacent, or I'm sorry, it's opposite over adjacent. So that's going to make this a squared plus x squared. And finally, for this expression, secant theta, we still have the same right triangle, all right, but secant theta is going to be adjacent, over the hypotenuse. That makes this x squared minus a squared. And this is how we actually do these trigonometric substitutions. The first thing to do is recognize what form do you have underneath the radical, and then you will apply the appropriate trigonometric substitution based on that. Now, these all these formulas can be found in your cheat sheet. So let me show you that. And here they are right here. Trigonometric substitution. If the integral contains the following root, given the substitution formula, and this just tells you exactly what to do. The square root of a squared minus b squared times x squared, you're going to rewrite it as x equals a over b sine theta, and cosine squared theta equals 1 minus sine squared theta. This is the exact one I just did, okay? So I think what we should do now is just go ahead and start doing some examples. So the first example here, sorry, I'm scrolling down. So here's our first example here. We're going to do the integral of the square root of 4 minus x squared all over x dx. Now, for me, first thing I do is draw my right triangle. Some people wait to do this towards like the middle of the problem. I just do it all the way at the beginning because I just want to get it out of the way. All right, so I have the form 4 minus x squared. So that is the square root of a squared minus x squared. And that tells me, okay, we're going to use the sine substitution here. All right, so sine, remember sine theta is going to be opposite over hypotenuse. So opposite of sine is going to be x, and then hypotenuse is going to be 2, because remember, it's 4 squared, so that's going to be 2, and then this will be 4 minus x squared. Now, a really easy way to determine why does the x go on the opposite side? Why does the 2 go on the hypotenuse side? Is remember, 4 minus x squared tells us that we're going to be using sine theta equals x over a. Okay? So, if I were to take sine theta equals x over a and just solve for x is going to equal a times sine theta. So that's like the easy way to kind of remember like how this goes, all right? Sine theta will always be x over a, and sine theta is opposite over hypotenuse. So the x goes on the opposite side, the 2 goes on the hypotenuse side. And now that we know what a is, I can erase this a and say, well, x is going to equal 2 sine theta. So dx will equal 2 cosine theta d theta. All right? So now that we have our substitutions, we're going to go ahead and we're going to do that. We're going to get the integral of the square root of 4 minus x squared all over x dx, and that changes into the square roots of 4 minus 2 sine theta. Let me give myself a little bit more space here. Make that larger. So it's going to be the integral of 4 minus the quantity squared of 2 sine theta, all divided by, remember that denominator is the letter x, so that's going to be 2 sine theta. And dx is now 2 cosine theta d theta. All right? So from here, it is just a humongous simplification game. That's all it is. So once again, just make sure you're taking your time with this. Make sure you're following the algebra, okay? So we're going to get the square root of 4 minus 4 sine squared theta all over. Well, here, the 2's reduce, so that's pretty nice. And I'm going to leave it as sine theta, cosine theta, d theta. I'm going to factor out that 4 underneath the radical. Okay, I know many of you may be tempted to write cosine theta over sine theta, and you want to convert that into cotangent. Don't do that yet. Just wait a second, okay? You want to do all your simplifying underneath that radical first. So we end up getting the integral of the square root of 4 times the square root. Now remember, 1 minus sine squared theta is cosine squared theta. All this is over sine theta, cosine theta, d theta. And just going from left to right, square root of 4 is 2. I'm going to move it out front. The square root of cosine squared theta is cosine theta over sine theta times cosine theta d theta. Now looking at what we have, it would be nice if we can make like a some sort of u substitution or something like that over here, but we cannot. So what we're going to do is we're just going to work with what we have. Cosine theta times cosine theta is cosine squared theta over sine theta d theta. And it would be really nice if I can just get rid of that sine theta in my denominator. And to do that, we're going to go back to say cosine squared theta is 1 minus sine squared theta over sine theta. And now, if you look at this from left to right, and I'm just going to write the algebra right here, I can rewrite this as 1 minus sine theta minus sine squared theta over sine theta. So I get 2 times the integral of 1 over sine theta is cosecant theta minus sine squared theta over sine theta is just sine theta d theta. And now I got a really nice integral I can do. So the integral of cosecant theta is going to be the natural log of cosecant theta minus cotangent theta. And if you're wondering where I got that, I will show you. Coming back over to here, I just kind of scrolled up. All right, give me a second. I got to find it. Here we go. It's right here. It's this one right here. So the integral of cosecant u du equals the natural log of the absolute value of cosecant u minus cotangent u plus a constant. So that's all I did. I just looked this up. It was right there for me. All right, back to our problem. We're going to finish it now. So we just did the integral of cosecant theta. Now, the integral of sine theta is negative cosine theta plus some arbitrary constant. And just to kind of clean this up a little bit, we get 2 times the natural log of the cosecant theta minus cotangent theta plus cosine theta plus c. Now, all of this is fantastic, but the problem, all right, but the problem here is our answer is in thetas. It was given to us, though, in terms of x. So, what do we have to do? You were absolutely right. I'm going to see if I can do this neatly. I'm going to copy and paste my right triangle that I drew all the way at the very beginning of the problem. Like I said, some people will do this towards the end. Some people will do this at the beginning. I'm old school. I like doing it at the beginning, because we're going to use this to our advantage to rewrite our problem in terms of x's. Let me see. I'm going to kind of shrink this down a little bit so I can see it. I think that's good enough. All right, so here we go. So going from left to right, we have 2 times the natural log. Now, cosecant theta, you got to remember, it's the reciprocal of sine theta. So if sine theta equals opposite over hypotenuse, cosecant theta is hypotenuse over opposite. So this is going to be hypotenuse, which is 2, over opposite, which is x. All right? So there's my substitution for cosecant theta. Okay? Minus cotangent. Well, cotangent, remember, tangent, everyone, is opposite over adjacent. So cotangent is adjacent over opposite. So cotangent is going to be adjacent square root of 4 minus x squared over the opposite, which is x. All right? Plus cosine is adjacent over hypotenuse. So it's going to be adjacent square root of 4 minus x squared over hypotenuse, 2. Oh, and I got a math error. This is 2 times the square root of 4 minus x squared over 2. Because remember, I had this 2. Oh, this is bad, and I'm not going to remake this video. So I have a 2, and I failed to distribute properly. So there's a 2 out front, and now the 2's reduce. And that's fine with me. Plus c. So let's clean this up. 2 times the natural log of 2 over x minus the square root of 4 minus x squared over x plus the square root of 4 minus x squared plus c. And there is our first trigonometric substitution answer. They can get lengthy like this. You just got to make sure you remember your trig identities and just basic algebra, because the only calculus thing that we did was right here. When we went from there to there, that was calculus. That's it. And even then, it wasn't even really a hardcore calculus. It wasn't difficult. We just looked it up. It's all about algebra and your trig identities. All right, let's try another one here. All right, here's our next problem. The integral of x to the third times the square root of 1 minus x squared dx. So if we want to use trigonometric substitution here, here's what we're looking at here. This has the form of a squared minus x squared. So that's telling us we're going to be making sine theta substitutions. So x equals a sine theta. Well, in this case, a is going to be 1. So dx is going to equal cosine theta d theta. So here's my substitutions. So I get the integral of x to the third times the square root of 1 minus x squared dx. We're going to convert that into the integral of, let me set this up real quick so I can make it look nice and neat. So wherever we see x, we're going to put sine theta. And then dx is no longer dx, it is cosine theta d theta. So cosine theta d theta. Now, it all comes down to just simplifying things, okay? So the first thing I'm going to do here is I'm going to take that sine theta to the third power, and I'm going to kind of separate it into sine squared theta times sine theta underneath my radical. All right. We end up getting 1 minus sine squared theta times cosine theta d theta. So sine squared theta is going to be 1 minus cosine squared theta times sine theta times the square root of 1 times, I guess we could just make it cosine squared theta times cosine theta d theta. And finally, when you look at this, all right, we're going to go ahead and use u substitution. We're going to let u equal cosine theta. du is going to equal negative sine theta d theta. And the reason why is because we can make the substitutions. So this is nothing more than just 1 minus u squared times the square root of u squared, which is u, times u times negative, let me write it like this, negative d theta. So here's what's happening, all right? We let u equal cosine theta. So substitute there, and substitute there. Right here is sine theta d theta, which that's what we needed to use u substitution. And finally, u times u is u to the second, and when you distribute that, you get u squared minus u to the fourth. Oh, I wrote d theta. This is supposed to be du. Times du with a negative out front. All right? So I guess if we wanted to, we could just say u to the fourth minus u to the second du by distributing that negative sign. I think that's going to be easier. Finally, integrate 1/5 u to the 5th minus 1/3 u to the 3rd plus a constant. And then you got to remember you used u substitution. So u, remember, it equaled cosine theta. So this is going to be 1/5 cosine theta all raised to the 5th minus 1/3 cosine theta all raised to the 3rd plus c. And then finally, if we draw a right triangle and we remember that we used a substitution of sine theta, sine is opposite over hypotenuse, so it's going to be x over a. Well, in this case, it's going to be 1. So that's going to make this (1 minus x squared). We could just go ahead and use cosine theta using our right triangle just to figure out what each one of these cosines have to be. So to make this real nice, sweet, and short, this is just nothing more than 1/5 times 1 minus x squared to the 5/2 minus 1/3 times 1 minus x squared to the 3/2 plus c. Now, just so we're aware, I've got the 5/2 and the 3/2 from the fact that this is really, let me write in a different color. 1/5 times the square root of 1 minus x squared to the 5th. All I did is said, well, the square root is really just 1 minus x squared to the 1/2 power. And when you have a power raised to another power, you multiply them together. So for the first, that's how I got that. And obviously for the second, this minus 1/3 is really the square root of 1 minus x squared, all raised to the 3rd. But the square roots can be rewritten as a fractional exponent, and 1/2 times 3 is 3/2. Now, hopefully, at least one of us was sitting there and going, when you looked at this, you went, wait a minute. There could have been a better way to do this problem. And the answer is 100%. In fact, sometimes, and what I mean by sometimes is a lot of the times, you want to slow yourself down. Because when you look at this, all right, you could have used substitution from the very start. And what I mean by that is this. If we let u equal 1 minus x squared, then adding x squared to both sides gives me x squared plus u equals 1. And finally, subtracting u from both sides gives me x squared equals 1 minus u. Now, looking at this, when I go ahead and take the derivative, I end up getting 2x equals negative du, or bringing the negative over here, I have this, negative 2x dx. Sorry, I forgot my chain rule. Negative 2x dx equals du. And when I go ahead and make that substitution, I get the integral of x cubed times the square root of 1 minus x squared dx is equal to negative 1/2 times the integral of x squared times 1 minus x squared times negative 2x dx. And then making our final substitution, you end up getting negative 1/2 times the integral of 1 minus u times the square root of u du. Distributing gives us negative 1/2 times the integral of u to the 1/2 minus u to the 3 over 2. In other words, convert this into 1/2 as an exponent. And finally, when you go ahead and integrate this, you're going to get negative 1/2 u, negative 1/2 times a quantity, u to the 3/2 multiplied by 2/3 minus u to the 5/2 times 2 over 5 plus a constant. And then finally, rewriting this back in terms of x's, you know what u equals. You let it equal 1 minus x squared at the very start. So you end up getting just negative 1/3, because these twos reduce when you distribute, times 1 minus x squared, all raised to the 3/2 power, plus, and then these twos reduce when you distribute, again, 1/5 times 1 minus x squared to the 5/2 plus c. So you end up with the same exact answer. I think the integral in this scenario is more difficult. And the reason why I think the integral in this situation is more difficult is because how many of us actually think to rearrange this thing right here? Not too many. All right, we're so used to just saying u equals this, and then the derivative of u equals the derivative of the function times its derivative dx, that we forget that you can actually manipulate that algebraically. Personally, with me, going all the way back up here, as soon as I see, oh, I can make this trig substitution, I'm going to do it. That's just me. Now let's do a couple more examples to finish off this video using the other trigonometric substitutions that we've learned. So I'm going to just go ahead, pause the video, scroll down, and get it all ready. All right, so I am back. Here's case 2. Case 2 is when we have tangent theta equals x over a. We have our right triangle here for reference. Remember, tangent is opposite over adjacent, so it's going to be x over a, going to be the opposite and adjacent sides respectively. Therefore, the hypotenuse will be the square root of a squared plus x squared if you were to solve this right triangle for the Pythagorean theorem. So the example that we have is going to be the integral of dx over the square root of 1 plus x squared. So remember, you're looking at the argument underneath the radical, and that is 1 plus x squared. So that fits our mold. So when I draw my right triangle here and put theta in the corner, nobody puts theta in the corner. Wait. Nobody puts baby in the corner. That's the reference. What is that? Dirty Dancing? It was a pretty good movie. Anyways, looking at this, tangent theta is going to equal opposite over adjacent. So the opposite is going to be x, and then adjacent is going to be 1. Therefore, the hypotenuse will be 1 plus x squared. So we kind of have everything we need to solve this problem efficiently. So let's go ahead. We're going to make our substitutions. In fact, you know what I'm going to do while I'm here? I'm just going to copy this because I know I'm going to need it later. So I might as well just copy it right now. Here we go. All right, perfect. So the integral of dx over the square root of 1 plus x squared is going to give us the integral of secant theta d theta over secant theta times d theta. Now, how do we get this? Remember, x equals tangent theta. All I did was I took tangent theta equals x over a and solved it for x. All right? So multiplied a by both sides. And a in this case is a 1. All right? Now, the derivative of x is dx. The derivative of tangent theta is secant squared theta d theta. So let me color code these for us, okay? Wherever you see x, you're going to replace it with tangent theta. So that goes down here. wherever we see dx, we are going to replace it with secant squared theta d theta. So here's the dx, here's the secant squared theta d theta right there. All right. So the method on how I did this was, remember, wherever I saw dx, I put secant squared theta d theta over the square root of 1 plus tangent squared theta. And 1 plus tangent squared theta is secant squared theta. All right? So it's secant squared theta d theta all over the square root of secant squared theta. The square root of secant squared theta is just secant theta. So that is how I got all this directly above. So I'm just going to rewrite it. Oops. And we're just going to simplify this a little bit further. We end up with the integral of simply secant theta d theta, which is a very easy integral to find. All we have to do is just go back to our chart. So here's our chart. And the integral of secant u is right here. So this is where we're looking right here. Can I highlight that? Oh, look at that. That's not too bad. So the integral of secant u du is equal to the natural log of the absolute value of secant u plus tangent u plus c. So all I'm going to do is just literally copy that down. So we'll go back to our problem. And like I said, I'm just going to go ahead and copy that down. So this is equal to the natural log of the absolute value of secant theta plus tangent theta plus c. And hopefully, I still have our reference right triangle, which is right there. Because now we can just go ahead and make our substitutions, okay? So the natural log, let's see, your secant theta is hypotenuse over adjacent because it's the reciprocal of cosine. So it's the hypotenuse over adjacent. So 1 plus the square root of x, or I'm sorry, the square root of 1 plus x squared. And technically this is over 1, so might as well just leave it there. Plus tangent theta is opposite over adjacent. So that's going to be x over 1 plus c. Or, just to make it look nice, we'll just drop the denominators. Call it a day. All right, so it's not too bad. Relatively straightforward. The thing to remember is, like I said, algebra, right angle geometry. That's basically it. All right, for the last problem here, we're going to do the last case. We'll do a definite integral on this one. So here's our last case. This will be case 3. Square root of x squared minus a squared. And I'm going to pause the video and go ahead and draw the right triangle and everything. All right, so here we are here. So we have the square root of x squared minus a squared. We have our reference right triangle. Secant theta equals x over a. Or if you solve it for x, x equals a secant theta. Now, there is one thing that we do have to be concerned with. All right? For x greater than or equal to a, we're going to take the absolute value of a tangent theta, which is equal to a tangent theta. Okay? On the other side, if x is less than or equal to negative a, then the absolute value of tangent theta is going to equal negative a tangent theta. The reason for this lies in this picture here. Here we go. All right. So the reason is it depends on the relationship that we have. So we may need to use some trigonometric identities, because theta can also be defined as the inverse secant of x over a. So we're going to need both reference triangles, since the values of some of the trigonometric ratios are going to be different depending on whether a is greater than or equal to, or I'm sorry, whether x is greater than or equal to a, or x is less than or equal to a. So we use these depending upon this scenario right here. It's actually a lot easier than you think. All right, you just gotta look at what you have. So here's our last example here. Like I said, we'll do a definite integral one. So we're gonna find the area of the region between f of x equals the square root of x squared minus 9 and the x-axis over the interval from 3 to 5. All right, so first thing we're going to do, just kind of sketch a little bit. So the square root of x squared minus 9 over the interval from 3 to 5. Let's see, this is 1, 2, 3, 4, 5. It's going to look something like this. And this is the area that we want right here. All right, not too bad. So our integral is kind of straightforward. All right, it's going to be the integral from 3 to 5 of the square root of x squared minus 9 dx. Now the big question becomes, okay, how do we make all these substitutions, stuff like that? Let me write this a little neater. There we go. I like the way that looks a lot more. So let's make our substitutions. X equals 3 secant theta. Dx, therefore, is going to equal 3 secant theta tangent theta d theta. So here's our trig substitutions. We will worry about the limits of integration later. We'll just worry about that later. First, let's just go ahead and make our substitutions here. So we'll get the square root of x squared minus 9 dx. Wherever we see the x, we're going to substitute in secant theta, or I'm sorry, 3 secant theta. So give myself some space. 3 secant theta. Wherever we see dx, we're going to put 3 secant theta tangent theta d theta. Now let's go through our algebra. The quantity 3 secant squared theta, or I'm sorry, the quantity 3 secant theta squared is just going to be 9 secant squared theta minus 9 times 3 secant theta tangent theta d theta. And we know 9 secant squared theta minus 9. We could factor out that 9. To give me 9 times secant squared theta minus 1 times 3 secant theta. I'm going to zoom out here a little bit. Secant theta tangent theta d theta. Separating the radical and then substituting secant squared theta minus 1 in for, I guess we can use tangent, or can we? Yeah, we'll figure it out. So first, square root of 9 is 3 times, We have another 3. You know what? I don't want to do too many moves at once. We'll keep it nice and simple. Times the square root of tangent squared theta. There's our Pythagorean identity. Then we still have all this off to the right-hand side. All right, now, 3 times 3 is 9. Square root of tangent is tangent theta. Secant theta, tangent theta, d theta. I think you can see where we're going with this. We have tangent theta times tangent theta. So that's going to be tangent squared theta. Secant theta, d theta. Using the techniques from the previous section, we're going to replace tangent squared theta with secant squared theta minus 1 times secant theta d theta. Let's go ahead and distribute secant to the third theta minus secant theta d theta. And finally, before we integrate, we're going to worry about the limits of integration. So remember, the limits of integration initially were from 3 to 5, but that dealt with x's, okay? So for us, we're now in theta world, all right? So what we're going to have to do is adjust these accordingly using our substitutions. So if x equals 3, then 3 equals 3 secant theta, all right? So remember, it was x equals 3 secant theta. Well, now it's 3 equals 3 secant theta, all right? So in this case, divide both sides by 3. And you ask yourself, where is secant theta equal to 1? Theta equals 0. So our first limit of integration is going to be 0. Okay? Now we're going to do the other one. And this one's a little bit more involved. Okay? But it's not bad. We can handle it. So if x equals 5, then 5 equals 3 secant theta, which means 5 over 3 equals secant theta. And then solving for theta, we use the inverse trigonometric function. Theta is going to equal secant inverse of 5 over 3. So our other limit of integration is secant inverse of 5 over 3. Okay? So now we can go ahead and we can finally integrate. So I am not going to go through this whole integral of secant theta, or secant to the third theta. And the reason is because we have our cheat sheet. And that's right here. So secant to the third of u du equals 1/2 times secant u tangent u plus the natural log of secant u plus tangent u, absolute value, plus a constant. Now, we don't have to worry about the constant, but we do have to worry about all this stuff, all right? So I'm just going to go ahead and write this out from left to right. So going back into our problem, we have 9 over 2 out front. All right, don't forget that. And this is going to be the natural log of the absolute value of secant theta plus tangent theta plus secant theta tangent theta. Now, that is the first integral. The integral of secant theta is going to be 9, because remember, this is the 9 right here. So you're going to distribute that to both. So it's just going to be 9 times the natural log of the absolute value of secant theta plus tangent theta. And all of this just do a line, will be evaluated between secant inverse of 5 over 3 and 0. So it's not as bad as what you think. All you got to do is just make these substitutions. But before we do that, let's simplify as much as we can. So up above, after you simplify, you should get 9 over 2 secant theta tangent theta minus 9 over 2 times the natural log of secant theta plus tangent theta. And this will be evaluated between 0 and the inverse secant of 5 over 3. And making all the appropriate substitutions, you get 9 over 2 times 5 over 3 times 4 over 3 minus 9 over 2 times the ln of secant theta. That's going to be 5 over 3 plus 4 over 3 minus 9 over 2 times 1 times 0 minus 9 over 2 times the ln of 1 plus 0. And when everything is all said and done, you end up with 10 minus 9 over 2 times the natural log of 3. Now, let me see here. I did kind of rush the end here because I don't want to make this video any longer than what it has to be. But just remember, because I know this looks like a lot, this is my upper limit. And this is my lower limit. And that's all I did. So, trigonometric substitution is definitely the more difficult of the techniques that we're going to be learning this first week. But all the other stuff kind of falls into place once you start your trig sub. You will notice, just like in all these problems, that like there's a lot of simplifying. Okay, a lot of simplifying. So just be careful with that. 99% of the time when I'm helping somebody with these problems, it's because of a sign mistake or a simplification error, not the calculus. So don't beat yourself up over the calculus part, but really pay attention on the algebra part. Just be careful with that. So I hope this helps, and I'll be back here for partial fraction decomposition.